Hi there, and thanks for coming to my talk. My name's Ross Walton, and I'm an application scientist at Unchained Labs. Today, I want to talk to you about how you can accelerate your antibody and formulation screens using Big Tuna for automated buffer exchange and Uncle for in-depth stability and aggregation analysis, all with just about 1 hour of hands-on time for setup. Old bicycles, or velocipedes as they were known in the 19th century, required a lot of hands-on time to use and a lot of energy to use. And actually, some of these were even hand-powered. Formulation screens can feel the same way, with lots of manual labor being necessary. Big Tuna and Uncle from Unchained Labs come together to help alleviate some of those pains. Big Tuna provides high-throughput automated buffer exchange and concentration, while Uncle gives you the ability to characterize and screen stability. That makes them the perfect pair for doing formulation screening. A lot of manual methods don't really cut it when you're talking in a formulation screening context for lots of different formulations or lots of different antibodies. Dialysis is a slow method that requires large amounts of buffer in order to be effective, but your antibody tends to end up getting diluted during the course of the buffer exchange. Centrifugation is much faster, but it can also be very tedious. And sometimes those membranes can actually get clogged during the course of the spin downs and the buffer exchange process. And setup for TFF, I mean, obviously TFF is a very effective buffer exchange method, but the setup can be quite complicated. And it's really most appropriate for higher volumes of sample than are necessary for a formulation screen. And that also makes it difficult to set up large numbers of buffer exchanges when you want to test a wide range of formulations during the course of a screening study. Big Tuna really steps in and helps meet some of those shortcomings of buffer exchange. It provides extremely flexible sample throughput, handling up to 96 exchanges during a single run, and also can handle a wide range of sample volumes, anywhere from 1 microliters up to 8 milliliters per well. Setup is very simple, and you just walk away and let the Big Tuna handle the rest of the buffer exchange. So you only need about 30 minutes of time to actually set up an experiment. Big Tuna can also handle extremely high concentrations of sample, up to 200 mg per mil of monoclonal antibody. Big Tuna is a filtration plate-based exchange system that uses these unfiltered plates. The unfiltered 96 has 96 wells, and each well contains 100 to 450 microliters of sample for doing a buffer exchange. And the filter sizes range anywhere from a molecular weight cutoff of 3 kilodaltons up to 100 kilodaltons. The unfiltered 24, like the name suggests, has 24 wells. And each one of these wells is, of course, deeper than the unfiltered 96, so it can handle larger volumes from 0.45 milliliters up to 8 milliliters. And it comes in a 10 kilodalton molecular weight cutoff. The filters are all made out of regenerated cellulose, and so they have a really low cost per sample. Buffer exchange in Big Tuna is totally automated. At the beginning of an experiment, you set the volume that should be removed from each well in each cycle, and you set the target percent exchange for the entire run. During the course of the run, Big Tuna uses positive pressure to filter out sample through the bottom of the well and combines that positive pressure with gentle orbital shaking, which prevents the buildup of proteins at that filter interface and also prevents membrane clogging. After set volume has been removed from the sample or from each well, which Big Tuna measures using an acoustic sensor, the well is refilled, and then another cycle of filtration and refilling happens until it reaches the complete exchange percent until it reaches the target percent exchange. At the end of a run, you can also do a concentration step, which removes, again, a volume from each well, but doesn't actually do, but then doesn't refill. So you can get to the concentration that you need for the end of the experiment. and then move on to whatever sort of characterization steps are necessary. So with Big Tuna, you can do 96 of these buffer exchanges, but then you've got 96 samples that you need to characterize. That can be quite difficult. But that's why Uncle is Big Tuna's BFF, because it can take the samples that were buffer exchanged using Big Tuna and do a stability screen with them. Big Tuna is an all-in-one multimodal stability platform that's built specifically for biologics. It contains two different lasers that are used to excite either a protein's intrinsic fluorescence or can be used to excite a variety of dye-based fluorescences. Now, both intrinsic fluorescence and dyes can be used to measure a protein's thermal stability. Since Uncle has full spectrum fluorescence detection, it can give you the full picture of your protein's thermal stability and unfolding behaviors with or without labels. Static light scattering, or SLS, is a way of identifying when aggregates start to form. And that data is actually collected at the same time as this fluorescence detection. Dynamic light scattering, or DLS, allows for even more detailed and finer analysis of the size and size distribution of particles in a sample. Now, all three of these detection methods can be operated isothermally at room temperature or at higher temperatures, or can be used during an entire thermal ramp. That way, you can thermally stress your samples to figure out which ones are most able to take the heat. Uncle delivers aggregation and protein stability results in about 2 hours with only 9 microliters of sample for up to 48 samples at a time. Part of the way Uncle's able to do this is with the sample holder, which is called the uni. Each one of these unis consists of 16 wells. They're actually 9 microliter cylindrical quartz cuvettes that are open at either end. All you have to do is pipette your sample into this uni, and then use the blue frame to close it up with a silicone gasket at either end of the uni. This silicone seal protects and isolates your sample so that you don't have to worry about cross-contamination between the samples in the different cuvettes, and you don't have to worry about any sort of evaporation or contamination happening during the course of an experiment. And it's really easy to seal up these unis. During a single run, Uncle can take 3 of these unis. So 3 times 16 means 48 samples possible per run. Now that we've looked at how many samples and how a experiment is set up in Uncle, let's take a look at some of the results that you can expect. So here we have an example of the thermal ramp of a protein, with the intrinsic fluorescence being shown in blue and the static light scattering of the 266 nanometer laser being shown in green. Intrinsic fluorescence is useful for looking at protein unfolding behaviors. And here you can see 2 very clear transition temperatures happening during the course of this thermal ramp. These transition temperatures are flagged as TM1 and as TM2, since they are, of course, melting temperatures. In green, you can see that the static light scattering has quite a sudden increase there at that aggregation temperature, or TAG, but it has a fairly flat baseline earlier on in the thermal ramp. With Uncle, you're able to look at both stability and aggregation during the course of the thermal ramp simultaneously. And the TM and TAG of protein are actually called automatically by the analysis software. So there's really zero-click analysis and makes the entire process very streamlined. During the course of a thermal ramp of a protein, the tryptophan residues of the protein, which are typically buried in hydrophobic pockets in the protein, become exposed to the aqueous environment, the aqueous buffer, as the protein starts to unfold. Now that actually causes a change in the overall fluorescence behavior of the protein. Typically what happens is that the fluorescence of the behavior decreases, as you could see from that animated GIF, and the peak of that fluorescence, you can see from about 300 to 350 nanometers, actually shifts towards higher wavelengths. which in this case are in the right side of the graph. And that's called a red shift. By looking at how this red shift happens, you can actually determine when a protein is unfolded and what its melting behavior is. However, not all proteins do this characteristic redshift behavior. In some cases during unfolding, a protein will actually blue shift. And some antibodies, some proteins don't even have tryptophan, fluorescent tryptophan residues. So you have to use dyes like Cipra orange in order to look at their protein, at their unfolding behaviors. Since Uncle has two different lasers, the 266 nanometer laser and the 473 nanometer laser, and also does a full spectrum fluorescence detection, it lets you set up the analysis, set up the experiment, do whatever you need in order to look at your particular antibody's unfolding behavior or your protein's unfolding behavior. During the course of a thermal ramp, small aggregates and large aggregates tend to form, but they don't necessarily form at the same temperature, and so need slightly different tools to characterize when they happen. With the 266 nanometers static light scattering, Uncle can detect smaller aggregate formation, since the smaller wavelength laser is more sensitive to those small aggregates. And then the 473 nanometer laser is useful for looking at larger aggregates. Since Uncle has both, you get very high sensitivity aggregation detection and a very wide dynamic range of sizes that you can detect. Along with static light scattering, Uncle has DLS, which is a way of looking at, in very fine detail, at the size and size distribution of particles within a sample. Here we have three example distributions of a protein during the course of a thermal ramp. And you should note that the x-axis in all three of these distributions is, of course, in log scale. In blue, we have a protein that is well-behaved at room temperature and is monodispersed and has a nice, well-defined average size at about 10 nanometers, which is typical for most antibodies. Along with that very typical Z average diameter, we also had a very low PDI. When the sample started getting heated up, it started to aggregate slightly. And that means that the Z average started to increase by a little bit, but also the PDI increase, or the spread of that, the width of that distribution started to increase. And that's an indicator of, in this case, a small amount of aggregates forming, either lots of small aggregates or a few large aggregates. By the end of the thermal ramp, here shown in yellow, you can see two very clearly defined peaks with an extremely high Z average relative to where it started and a very wide PDI, very wide distribution. Now, the nice thing about DLS is that you can actually determine the size and size distribution in seconds. You don't need a large amount of time to look at sizes, which makes it unique amongst a lot of other techniques that are used for looking at average size of particles in solution. For this experiment, we did a formulation screen in which we took 5 commercially available monoclonal antibodies and buffer exchanged them into 3 different buffers using Big Tuna. After we did that buffer exchange, we looked at the thermal stability and aggregation behavior of those 15 samples in Uncle using the TM, TAG, and DLS application. For the Big Tuna, we used the unfiltered 96 with a 10 kilodalton molecular weight cutoff and had an initial and final volume of 300 microliters because we didn't want to do a concentration step in this particular case. Our target concentration, our target exchange percentage was 96%, and we had Big Tuna remove 66% of the volume, or 200 microliters, from during each cycle. Here you can see a table of the antibodies that we used, their starting buffers, and the final buffers that we exchanged into, which were PBS at pH 7.4, a 25 millimolar sodium acetate buffer at pH 4, and then that same 25 millimolar sodium acetate buffer at pH 4, but with 130 millimolars of sodium chloride spiked in. Big Tuna is just a simple load and go method, requires used about 30 minutes of hands-on time in this case in order to set up the experiment and pipette in the sample. And then Big Tuna handled the rest of it. And the total runtime for this exchange was 3 hours and 45 minutes. At the end of a run, Big Tuna will actually report the total percent exchanged for each one of the wells. And you can see it here. And in every case, we got at least to that 96% target exchange. After exchange, we loaded the samples into Uncle, and we started looking at the stability of the various samples. And we found a few interesting conclusions. First, the monoclonal antibodies were significantly less stable in that 25 millimolar sodium acetate buffer with the 130 millimolar sodium chloride. For those of you unfamiliar with looking at TMs, a higher TM indicates a more stable antibody or a more stable formulation. And here you can see that all of the antibodies that we screened had higher TM1 and higher TM2 in the salt-free buffer versus the salt-containing buffer. And that difference ranged anywhere from about 5.8 degrees Celsius up to 12.4 degrees Celsius. So all that indicates that all of these antibodies were more stable in that salt-free buffer. But you don't just necessarily, in a given study, you might not necessarily be comparing one buffer to another, but rather be comparing one protein to another. And you can do that with Uncle as well, because different proteins have different stabilities. Here, looking at cetuximab and rituximab in PBS, looking at both unfolding and aggregation, you can see that rituximab had higher TM and TAG than cetuximab did. TMs are shown on the left with the gray drop lines indicating the TM, and then the TAGs are shown on the right with these yellow drop lines. Like with a TM, a higher TAG means that a protein is more stable and less prone to thermal aggregation. So buffers have an impact not just on the exact TM, but also on more general unfolding behaviors. Here we have NISTmab, which is the NIST monoclonal antibody reference material in PBS at pH 7.4 and sodium chloride sodium acetate at pH 4. In PBS, NISTmab has 2 TMs, but in the acidic sodium acetate buffer, NISTmab actually had 3 TMs. That change in unfolding behavior can be quite interesting, very important for a formulation study, and is an indicator that NISTmab in PBS might be unfolding cooperatively, whereas in that acidic buffer, NISTmab is no longer unfolding cooperatively. So TAGs shift depending on the buffer as well as the TM. Here, you can see trastuzumab in PBS at pH 7.4 had an aggregation temperature that fell almost smack in the middle between its 2 unfolding temperatures. But if you compare that to trastuzumab in the starting buffer, you can see that that aggregation temperature came up just a bit after that second unfolding event, that TM2. And that's despite TM1 and TM2 both being about the same between PBS and the starting buffer. TM1 was about 70 degrees Celsius in both of these buffers, and TM2 was about 78 or 79 degrees Celsius in both of these buffers. When aggregation happens can be just as important to know in the course of a thermal ramp as when unfolding starts to occur for a given monoclonal antibody, and is an important output for a formulation screen. As we talked about earlier, with Uncle, you can actually look at the formation of both small and large aggregates, which happen at slightly different temperatures for most monoclonal antibodies during the course of a thermal ramp. Here, we can see NISTmab in PBS starts having small aggregate formation at around 79 degrees Celsius based on the static light scattering of the 266 nanometer laser, which is sensitive for small aggregates. And then large aggregates start forming a little bit later, probably at around 81 or 82 degrees Celsius, which we determined based on the static light scattering of that 473 nanometer laser. We're also able to confirm the formation of these large aggregates using DLS, which you can see the two different DLS distributions at 15 degrees Celsius and 95 degrees Celsius on the right. In blue at 15 degrees Celsius, there's a nice sharp peak with an average diameter at about 10 nanometers. And in this case had a very low PDI, less than 0.1, which indicates a nicely monodispersed and high quality sample at the beginning of this thermal ramp. At the end of the thermal ramp, on the other hand, the Z average had increased to over 1,000 nanometers. And you can see how far the peaks shift, this new peak that formed, how far all the signals shifted over to the right of this graph, indicating formation of lots of large aggregates during the course of this thermal ramp, which is exactly what we expected based on the static light scattering results. What was interesting was that we found that one of the buffers of NISTMAP actually seemed to either limit or prevent this aggregation event. So NISTMAP in its starting buffer, when we did a thermal ramp, showed an increase above baseline in the SLS 266 signal, which of course is an indicator of the formation of small aggregates. However, the SLS 473 signal stayed more or less at its baseline. It had never increased significantly during the entire thermal ramp up to 95 degrees Celsius. Now that was puzzling to us, but using DLS, we were actually able to find out what was going on. So again, as in the previous slide, at 15 degrees Celsius, we saw a very nice sharp peak centered at about 10 nanometers, which is what we expected for this protein. But at 95 degrees Celsius, we saw similarly a very sharp peak in the intensity distribution of the DLS results, but this one was centered at about 13 nanometers of Z average. Now, this is an indicator that no large aggregates formed during this experiment, and we were able to have two different outputs, both of which led to that same conclusion. So using buffers to control aggregation seems to work quite well in certain cases and for certain monoclonal antibodies. Uncle and Big Tuna combined lets you move fast with your formulation screens, using less hands-on time, which is great, gives you more tools for looking at your protein's behavior in a wider number of formulations, so you can really know in depth as to what's going on with your proteins and therefore get better answers and make better decisions about which proteins and which formulations should move forward in your screens. So I hope that by listening to this talk, you can understand how you can use Big Tuna and Uncle combined to get rid of all that manual labor, leave it behind in the 19th century, and instead write fast and in style with automation. Thank you for your attention. I'll be happy to take any questions you might have.